In this video, we're going to start looking at series in general and then more specifically geometric series. So I want to start by looking at the sequence an equals 1/3 to the n, and another sequence Sn equals the sum k equals 0 to n of 1/3 to the k. All right, and so both of these are sequences. The one on the left is what we've been dealing with quite a bit. So we can look at this and say, okay, A0 is 1 because it's 1/3 to the 0. A1 is 1/3. A2 is 1/9. A3 is 1 over 27. A4 is 1 over 81, and so on. And so we can think of this in that way, or we can think of it as a list of numbers: 1, 1/3, 1/9, 1 over 27, 1 over 81, and so on. And so we have this infinite sequence, and it's pretty clear from the list of numbers, and it's clear from the techniques that we've been dealing with that 1/3 to the n, that sequence converges to 0. And so we've been doing all these techniques in order to show whether a sequence converges or diverges. So we know certain things about exponentials, like 1/3 to the n. We know things about power functions. We know how to use the squeeze theorem. We know how to use L'Hopital's rule when necessary. And we can show that sequences are bounded and monotonic. And so all the stuff we've been doing has been dealing with sequences like this one on the left. The significance of that is that it's easy to look at that and say, if I wanted to know a random term like A75, it would be easy to calculate that without calculating any other terms in the sequence. Okay, the one on the right is still a sequence, so it's S sub n, and we've talked about these. We talked about these a little while ago, but I want to jump down and figure out what S3 is, and then go back and find the other ones. So the notation looks a lot more complicated than the one on the left, and it is a little more complicated. But if you notice on S sub n, and then when we talk about S3, the 3 is replacing n, the 3 is not replacing k. So what S3 means from that notation is it's the sum k equals 0 to 3 of 1/3 to the k. And then sigma notation means we would plug in k equals 0, k equals 1, k equals 2, and k equals 3 and add those. So if I plug in k equals 0, I get 1. If I plug in k equals 1, I get 1/3. K equals 2 gets us 1/9, not 1/3. K equals 3 gets us 1 over, and plus, gets us 1 over 27. And then if we add those up, we get 40 over 27. And so that is S3, but we're adding the terms in the sequence on the left in order to get a single term in the sequence on the right. So let's go back and do S2. So S2 is the sum k equals 0 to 2 of 1/3 to the k. That means, okay, plug in 0 and we get 1. Plug in 1 and we get 1/3. Plug in 2, we get 1/9. We stop at 2 because that's the number on top of the sigma notation. If you add those, you get 13 over 9. We'll go ahead and get S1. That's the sum k equals 0 to 1 of 1/3 to the k. So if I plug in 0, I get 1. If I plug in 1, I get 1/3, and we get 1 1/3 or 4/3. Go back and get S0. That's the sum k equals 0 to 0 of 1/3 to the k. And that means we just plug in 0 and stop, so we get 1. Sorry, that's running a little together, but we get 1 there, and then we'll get 1 more down here. So let's get S4. That's the sum k equals 0 to 4 of 1/3 to the k. That's going to be 1 plus 1/3 plus 1/9 plus 1 over 27 plus 1 over 81. And when we add those, we get 121 over 81. Okay, and so the sequence on the right is the sequence of numbers 1 4/3, 13/9, 40 over 27, 121 over 81, and so on. This is called a sequence. It's still a sequence. It's a sequence of partial sums. And so a series is the limit of this, or a series is the infinite sum of the one on the left. That's so if we added up 1 plus 1/3 plus 1/9 plus 1 over 27 plus 1 over 81 plus 1 over 243 plus whatever's next, and we keep going on forever, the series is the sum of the infinite number of terms. That is the limit of the one on the left. So, I'm sorry, it's the limit of the one on the right. It's a little unclear looking at these fractions what happens to this series. If you look at decimal representations of this, 4/3 is about 1.3333. If we round to 4 decimal places, 1.3 repeating. 13/9 is 1.4444. 40 over 27 is about 1.4815, and 121 over 81 is 1.4938 if you round to 4 decimal places. And so it's not entirely clear what's happening to the sum on the sequence on the right. It looks like maybe it's going to 1.5, but we can't possibly know that just by looking at those numbers. So the goal of what the next part of the course is how do we figure out what a sequence like this is doing? The more complicated part of the thing on the right is, even though it would be easy, like we said earlier, to come up with A75 without determining 75 terms, we just need to find one term. Here, it would be difficult to come up with, not impossible, but it would be difficult to come up with S75. There's not a formula that's direct from what we've got where we can just plug in 75 and get it without adding 75 or 76 terms together and getting the total. And so we're going to look at a lot of different series where sometimes it's not possible to get an easy closed form for finding like S75, a closed form meaning one like this one on the left where you can just plug it in and get an answer without sigma notation. Sometimes that's impossible. For geometric series, which is the first type, it is possible. And so we're going to go through that on the one on the right here in just a second, but let's talk about specifically why this is a geometric sequence. So if you look at the one on the left, this is called a geometric sequence because in order to go from one term to the next, the pattern is that you multiply by the same thing. So you multiply to go from 1 to 1/3, you multiply by 1/3. To go from 1/3 to 1/9, you multiply by 1/3. To go from 1/9 to 1 over 27, you multiply by 1/3, and so on. The one on the right is the geometric series, where the things you're adding are from a geometric sequence. So here we're talking about a geometric series. The limit of this is the geometric series. Not clear from the list of numbers that it's a geometric series, but the way they were obtained was by adding the terms in the geometric sequence. That means it's a geometric series. I'm trying to get it to erase, man, my bad. So let's look at a way to get a formula for the nth partial sum on the one on the right. So we're going to scroll down, and we're going to still use that series. So we've got Sn is the sum k equals 0 to n of 1/3 to the k. And so the goal is to get a formula that does not involve sigma notation that would represent this partial sum. And so what we're going to do here is not what we normally do. We're going to do it for this, and then we're going to do it for a general geometric series. But the goal of this is so that we can skip this in general. So Sn is the sum from 0 to n of 1/3 to the k. So if I plug in 0 for k, I get 1. If I plug in 1, I get 1/3. If I plug in 2, I get 1/9. I plug in 3, I get 1 over 27. And assuming n is very large, I keep going until I get 1 over 3 to the n, or 1/3 to the n power. And this stops. So we're looking at what happens as n goes to infinity, but this actually stops because n is just some large number. Maybe it's 1,000,000 or something bigger than that. The term right before this would have been 1/3 to the n minus 1, because that's the an minus 1 term. Okay, and so we're trying to get a formula for Sn where we don't need to add up 75 or 76 or n terms in order to do the problem. And so what works well here is to multiply both sides of the equation by the thing you're multiplying. And so let's make a quick comment about that. The thing you're multiplying by up here is 1/3. The thing that you're multiplying, that's called the common ratio. And so here the common ratio is 1/3, and the technique that works on this to come up with a formula is to multiply both sides by the common ratio. So if I do that on the left, 1/3 times Sn, you just write as 1/3 Sn. If I do that on the right, the 1/3 distributes, and so 1/3 times 1 is 1/3. 1/3 times 1/3 is 1/9. 1/3 times 1/9 is 1/27. And then 1/27 times 1/9, times 1/3 is 1/81. And so it's weird, but when I'm multiplying by 1/3, this one becomes that 1/3, this 1/3 becomes that 1/9, and so on to the right. The 1/27 becomes 1/81, and then we're going to keep going and get whatever's next, 1/243, and so on. And now if I multiply 1/3 by 1/3 to the n minus 1, up here on the right is what happens. So 1/3 times 1/3 to the n minus 1, we can think of that as 1/3 to the first times 1/3 to the n minus 1, and we add powers. So if you add powers, 1 plus n minus 1 is n, and so this is equal to 1/3 to the n. So we get 1/3 to the n, but that comes from the 1/3 to the n minus 1. Using similar algebra, 1/3 times this last term, 1/3 to the n, is 1/3 to the n plus 1. But again, that came from the 1/3 to the n above. And so it's important that this then stops. So that's the end of the sum, or that's the end of the second line here, 1/3 times the sum. And then we want to look at what lines up here. So I've made it look like everything lines up. Like 1/3 over here is right above 1/3, 1/9 is right above 1/9, and 1/27 is right above 1/27. And then we want to figure out, okay, what actually lines up and what doesn't. So the 1 in the top line, there's actually nothing directly under the 1 because the first term in the expansion on the bottom is 1/3. The 1/3 again lines up with 1/3. The 1/81 does line up with 1/81 that would have been in the top line, because even though I didn't write it in these dots, this 1/27 is there, but the next one would have been 1/81. So that does line up. The 1/3 to the n minus 1 also lines up. So the one before that here would have been 1/3 to the n minus 2. When I multiply that by 1/3, I would get 1/3 to the n minus 1, so that does line up. The 1/3 to the n plus 1 at the end does not line up because the top sum did stop at 1/3 to the n. So everything lines up except for the 1 at the beginning and the 1/3 to the n at the end of the top line. I'm sorry, the 1/3 to the n plus 1 at the end of the second line. That does line up. This does not line up. Okay, so everything else lines up. So what's smart here is to subtract the equation. So we treat this as a system of equations, which it is, and so we can subtract the two equations. And the reason that's smart is because then a ton of terms will cancel out. So we put a big minus sign over here, we're going to subtract them. If I do that on the left, I get 1 Sn minus 1/3 Sn. Well, 1 minus 1/3 is 2/3, so I'm just combining like terms, and we get 2/3 Sn. When I do that on the right, everything cancels except for two terms. So the 1/3, the 1/9, the 1/27, all of the middle stuff cancels. So 1 is left because it's 1 minus 0, and then minus 1/3 to the n plus 1 is left because we have nothing there, and then we subtract it on the top. The goal of all of this is to get a formula for Sn. So Sn is then 3 halves, because we multiply by the reciprocal, times 1 minus 1/3 to the n plus 1. Okay, so this formula is real important because what that does is it gives us a way to get the terms up here, like S4, by plugging in 4 to that formula rather than adding up 5 terms, or adding up 1 plus a ninth and so on, or 1 plus a third plus a ninth and so on. So if I were to plug in S4, that's 3 halves. If I plugged in 4, I get 3 halves times 1 minus 1/3 to the 4 plus 1, so to the 5th. And then if I simplify that, I do get, and you should verify this, but I do get 121 over 81, which is what we got up there. That's not especially useful for S4, but if I wanted you to find S75, like we were talking about before, that would be a lot easier to do. We could plug that in here and not have to calculate 76 terms and add them up. The main thing is we're trying to figure out whether the series or sequence converges or diverges. And so we're looking at the limit of this as n approaches infinity. Well, if we think about what's going on, as n approaches infinity, we have 3 halves, that's going to stay the same. We have 1, that will stay the same, but now it's 1/3 to the infinity, which will go to 0. That means this is going to converge to 3 halves, which means that this infinite series, this infinite sum, converges to 3 halves. All right, that's a long proof that this series on the right, this Sn over here, that converges to 3 halves, which we were kind of guessing by looking at these numbers. There's a much simpler proof later, and we'll get to that, but I want to talk about the notation for a second. So we can talk about the notation this way. We can say the limit as n goes to infinity of Sn is equal to 3 halves. We can say Sn converges to 3 halves. We can say the limit as n goes to infinity of the sum k equals 0 to n of 1/3 to the k is equal to 3 halves. All of those are the same, but what's standard to write is that the sum k equals 0 to infinity, so instead of putting n there, we put infinity. The sum k equals 0 to infinity of 1/3 to the k is equal to 3 halves. And so this is saying that that series converges to 3 halves. That's the notation that is standard, but it's the same thing as if we mean these 3, or the same thing we would mean if we wrote those 3. It's saying that this sequence of infinite, the sequence of partial sums, the infinite sequence of partial sums, that converges to 3 halves. And it's also saying that if we add an infinite number of terms, 1 plus a third plus a ninth plus 1 over 27, and so on forever and ever, that is equal to 3 halves. That's weird to think about, and we'll talk more about how that's even possible in a little bit, but I want to do this in general for a geometric series first. Okay, so a general geometric series is one that takes the form the sum k equals 0 to infinity of a r to the k. And so any geometric series can be put into this form, and there's a little bit more about how that works in the video that's on writing formulas for sequences. It's in the playlist that's called prerequisite material for sequences. It talks about how to write formulas for several different types of sequences, but one of them is geometric. But this is a geometric series because we're adding up a geometric sequence. R is called the common ratio. That's the thing you multiply by every time. And so what we're going to try to do is come up with a formula for the nth partial sum. For any series in general, so this is the infinite sum, k equals 0 to infinity. Sn is the sum k equals 0 to n of a r to the k. And so instead of going from 0 to infinity, we actually stop at n, and we think of n as just being a large number, and what we want to ultimately get is the limit as n approaches infinity, which would be the sum of the infinite series. So we're going to do a similar approach to the one we did a minute ago, where we do a system of equations. And so Sn, if I plug in 0 to the expression up here on the right, is a r to the 0, but r to the 0 is 1. So we get a. and then plus k equals 1 gets us ar to the first, k equals 2 gets us ar squared, k equals 3 gets us ar to the third, k equals 4 is ar to the fourth, ar to the fifth, ar to the sixth, and so on. And so the last term in the expansion would be ar to the n, where n is just some large number. And the one right before that, kind of like the one we were doing a minute ago, is ar to the n minus 1. Okay, so n again is a huge number. We're talking about the limit as n goes to infinity, but this is the nth partial sum, the sum from 0 until n. So above, on the one where we were talking about 1/3 as the common ratio, we multiplied by 1/3 because what it did is shifted all the terms so that when we subtracted them, almost everything on the right-hand side subtracted out. So here, we're going to multiply by the common ratio r, and that gets us r(Sn). So if I multiply r on the right-hand side, the r distributes. So r times a is ar, but again, like above, that ar is coming from the a in the line above it. Whoops, ar. And then r times ar is ar squared, and again, that's coming from the ar in the line above it. R times ar squared is ar to the third. R times ar to the third is ar to the fourth. Ar to the fifth, ar to the sixth, and so on. R times ar to the n minus 1. We can look at that on the top right over here. And so r times ar to the n minus 1, we can think of it as r to the first times ar to the n minus 1. You add the powers, and so we get ar to the n. And so r times ar to the n minus 1 is ar to the n. So that comes from there. And then r times ar to the n is ar to the n plus 1. Okay, and so this is going to work the same way that the example above worked. We're going to end up subtracting the two equations so that a ton of stuff cancels out, but we want to figure out, most of this lines up, we want to figure out what actually does line up and what doesn't. So obviously like ar lines up with ar right here, ar squared lines up with ar squared, and so on. A, it turns out, does not line up with anything because that became ar on the bottom line. Ar to the n minus 1, I'm sorry, ar to the 4 does line up, and so ar to the 4 would have been the next term in the line up here, and so that does line up with the ar to the 4 underneath. Ar to the n minus 1 also lines up because the one before that up here would have been ar to the n minus 2, and so when we multiply by r, we get ar to the n minus 1. And then it's important that ar to the n plus 1 at the end does not line up with anything. Let's make that a 1 there. So the ar to the n plus 1 does not line up at the end. And now everything lines up except for the first term on the first line and the last term on the second line. So we're going to subtract everything. So if I do that on the left, we can do some creative subtraction and write it as 1 minus r times Sn, where we're combining the coefficients. On the right-hand side, everything cancels except the a on the top line and the ar to the n plus 1 on the bottom line. That's subtracted because we're taking the top line minus the bottom line. The goal is to find a formula for Sn that doesn't involve adding up a bunch of terms. And so we divide by 1 minus r to solve for Sn, and we get a minus ar to the n plus 1 over 1 minus r. So now the idea is this is the nth partial sum for any n for any given geometric series. And so what we're looking at is what is the limit of this as n approaches infinity. So we're going to write it this way. We're going to say, okay, what is the limit as n goes to infinity of Sn? That's the limit as n goes to infinity of a minus ar to the n plus 1 over 1 minus r. Now think about this expression as n approaches infinity. So the a at the beginning does not change. Ar to the n plus 1 does as n gets bigger. The 1 minus r on the bottom doesn't change as n approaches infinity. So this is the part that determines whether the sequence converges or diverges. If r was like 4 and you have 4 to the infinity, that term goes to infinity, which means the whole sequence here would diverge. If r was like 1/3, like it was in the problem above, 1/3 to the infinity goes to 0. So what happens is the thing I've got circled goes to 0 if r is between -1 and 1. Then the circled part goes to 0. So this is equal to a minus 0 over 1 minus r if this is true. If r is outside of those values, ar to the n plus 1 goes to either infinity or negative infinity or alternates. If r is 1 or if r is -1, then it's a little bit more complicated, but in both of those cases it ends up diverging, and we'll kind of see those more later. But in this case, if r is between -1 and 1, this converges, and it converges then to a over 1 minus r. Okay, so that's a really big result. So geometric series. So any series in the form, the sum k equals 0 to infinity of a r to the k, any series in that form converges if r is between 1 and -1. But the more compact way to write that is the absolute value of r is less than 1. So that means r is less than +1 and it's bigger than -1. It diverges otherwise. So it diverges if the absolute value of r is greater than or equal to 1. And when it converges to a over 1 minus r. That's going to make these problems a lot easier to do because we went through the proof that we just went through for the general series ar to the k. We now don't need to go through that system of equations every time. It'll work to just use this result every time. And so we're going to look at some examples next. Sorry, that bothered me. That didn't look good. We're going to look through some examples next where we use this result. So okay, so directions would be show whether the series converges or diverges. And then if it converges, find its sum. Okay, and so we're going to start with the one that we did earlier, which was the sum k equals 0 to infinity of 1/3 to the k. So remember, we went through an entire system of equations to do that. Now with this result, we don't need to do any of that. We can say, okay, this is geometric. And so think about why we know that that's true. So we're going to say in our proof or in our explanation, we're going to say this is geometric. You don't really need to explain that as long as we're right about that. We know it's geometric because it's exactly in the form a r to the k. A is 1, r is 1/3, and it's exactly in the form in the box at the top of the screen. So this is geometric. If you look at the result that we've got, what determines whether or not the series converges? Does A determine that? Does R determine that? Does K determine that? Does something else determine that? And so what determines whether or not it converges is R, and more specifically the absolute value of R. So we say what that is. So the absolute value of R is 1/3 in this case. So we write that. We say absolute value of R is 1/3. And then what about that determines whether or not it converges? So it converges if this is less than 1. It diverges if it's greater than or equal to 1. So the fact that 1/3 is less than 1 means we know this converges. That's the answer or the explanation for the first part. That's our proof or our explanation as to why the series converges. We say that it's geometric, we say what the absolute value of R is, and we say what's important about that. What's important about that is not, for instance, that it's positive. What's important is that it's less than 1. Because of that, it converges. Now, if it converges, we're asked to find the sum. So the sum, we'll just call it S, the sum is equal to A over 1 minus R. Well, here A is 1, R is 1/3, and so it's 1 minus 1/3, which is 1 over 2/3, and then that's 3/2. So this is the proof that it converges to 3/2. Or we could write the sum k equals 0 to infinity of 1/3 to the k equals 3/2. So the answer to the first part of the question, show whether it converges or diverges, is converges. Its sum is 3/2. This is much quicker than going through the system of equations, but because we spent the time doing that with AR to the k, we don't need to do it in general, or we don't need to do it every time. All right, let's look at another example. Okay, so if we have the sum k equals 0 to infinity of 4 times 3/2 to the k, again, we can say this is geometric. It's clear that it is because it's in the form AR to the k. What's important about whether it's geometric or not is that the absolute value of R is 3/2. The significant part of that is that that is greater than 1. So the series diverges. You can calculate A over 1 minus R, but it would not mean anything for this series. So if you go back up and look at this sum, this limit right here, the part I've circled, if R is 3/2 goes to infinity, which means that dominates the fraction and you end up getting either infinity or negative infinity. Here you'd get infinity. So the series diverges. So if you calculated A over 1 minus R, you can do that computation, but it would actually not mean anything. So number 3, again, directions show whether the series converges or diverges. If it converges, find its sum. So let's look at the sum k equals 0 to infinity of 8 times 1/2 to the k. So we say, okay, this is geometric. The absolute value of R is 1/2. What's significant about that is that that's less than 1. So the series converges. Its sum is A over 1 minus R, which is 8 over 1 minus 1/2. That's 8 over 1/2, which is then 16. So it converges to 16. So I'm going to write it over here. The sum part is that the sum converges to 16. Okay, so let's try the sum k equals 2 to infinity of 81 times 1/3 to the k. And so if you have a minute, pause the video, work this problem, so do the proof part, and if it converges, find the sum. And then when you're done, unpause it and watch me. It's real important to try this one before you watch me do it. Okay, so this problem starts just like the others. This is geometric. The absolute value of R is 1/3, which is less than 1. Cannot read the 1/3, so let's fix that. So 1/3, which is less than 1. And so then the series converges. It's important that when we do the sum, that we actually get 9 over 1 minus 1/3. And so if you worked this and you did get 9, great. If you didn't, I want you to think first before I explain it. So pause it and see if you can determine how I got 9 rather than 81 in the numerator of that fraction. Okay, so the way that I get that is I plug the initial value of k in. So 81 times 1/3 squared, that's 81 times 1/9, which is 9. That's the numerator of the fraction. If you go back and look at the proof, this A comes from whatever's here being left over. And so it's whatever the first term in the expansion is. When the sum starts at k equals 0, Then the first term in the expansion is AR to the 0, which is A. That's why this result is correct, because this starts at k equals 0. The problem that we're doing starts at k equals 2, which means if we were to go through the entire system of equations, the first term in the expansion would be the term for k equals 2, not k equals 0. And so the top of the fraction is 9, not 81. From there, it's easy to simplify. We get 9 over 2/3, which is then 27 halves. And so this converges to 27 halves. Okay, so you try this problem and make sure you can do the problem correctly. And let's do the sum. K equals, we'll do 1 to infinity of 5 times 1/3 to the k. So try that, pause it, try the problem, and then check it with me in a second. Okay, so to show this, we say, okay, this is geometric. We say the absolute value of r is 1/3. It's important that that's less than 1. So the series converges. Its sum is a over 1 minus r, but a is misleading. A is the first term in the expansion. First term in the expansion would be 5/3 over 1 minus 1/3. That's 5/3 over 2/3, which simplifies to 5 halves. So this series converges, and it converges to 5 halves. Okay, so now you need to practice this a good bit. So I'll talk to you in email or over Hangouts about a worksheet that you should start working on. We should do some of the basic ones, and then in the next video or next class, we will move into some more complicated examples of this. All right, thanks for watching.